Thank you for joining this contributed ICALP talk on the power of ordering in linear arithmetic theories. I'm Christoph Haase from University College in London. What I'm going to present is joint work with Dmitry Chistikov from the University of Warwick. Our paper is about logical definability in linear arithmetic theories. Logical definability is an area in mathematical logic that studies what sets are definable in a given first-order structure. It has led to many remarkable results. So, for instance, the MRDP theorem, which established that existential formulas of the natural numbers with addition and multiplication define recursively enumerable sets. Another result of this kind is that the integers are definable in the first order theory of the rationals with addition and multiplication, a result that was established by Julia Robinson in 1949 and which meant that this theory, logical theory, becomes undecidable. In computer science, we're also often interested in structural properties of sets definable in a logical theory. And one of the seminal results in this area is the one by Ginzburg and Spanier from 1964, which shows that formulas of Pressburger arithmetic, which is the first order theory of the natural numbers with addition and multiplication, define semi-linear sets, which in dimension 1 are just called ultimately periodic sets. So an ultimately periodic set is a subset of natural numbers such that there is an initial segment in which the natural numbers can be arbitrary, but at some point after a certain threshold, this set becomes periodic, so meaning we find a period P such that whenever an element is in the set, then also the element plus the period is in the ultimately periodic set. In our paper, we studied the computational complexity of a definability problem, which in general terms can be phrased as follows. We're given a first order structure A and some substructure B and some set S that is definable in A, and we want to decide whether S is also definable in the substructure B. Again, this is a topic that has been studied a lot in computational logic. A seminal result by Mushnik, which was established in the early 90s and published in 2003, says that it is decidable in elementary time whether a set that is definable in Büchi arithmetic is definable in Pressburger arithmetic. So Büchi arithmetic is a superstructure of Pressburger arithmetic and allows for defining all sets of integers that can be encoded as regular languages. In 2010, Geoffroy and Frigari looked at these definability questions for fragments of Pressburger arithmetic. They considered the question of deciding whether a set definable in Pressburger arithmetic is definable in so-called weak Pressburger arithmetic. In their setting, Pressburger arithmetic is the first order structure of the integers together with addition and order, and weak Pressburger arithmetic does not have the order relation but only an equality relation. They showed that the definability question in this setting is decidable in non-elementary time by establishing a geometric characterization of the sets definable in weak Pressburger arithmetic. In our paper, we build up on the work of Geoffroy and Frigari and study computational complexity aspects of their weak definability problem, not just over the integers, but also over the rationals. So just to tie down a bit of notation for the rest of this talk, so by weak Q definability, we mean the problem of deciding whether a set definable in linear rational arithmetic is definable in its weak counterpart, where we don't have the order relation available, but just an equality relation. And the weak definability, Z definability problem just refers to the problem that was studied by Geoffroy and Frigari. We will use the terms Pressburger arithmetic and linear integer arithmetic synonymously. So let's just discuss some facts about weak definability. Well, the first fact we need to establish is that the problem is actually not trivial, but this is a standard result in mathematical logic. So if we look at the mapping h that is defined here, which takes an integer and maps it to its negative, then this mapping is an automorphism for weak linear arithmetic theories, but it fails to be one in the presence of the order relation. And as a result, this fact establishes that weak linear arithmetic theories, both over the integers and over the rationals, are strictly less expressive than their counterparts in which the order relation is present. Moreover, it is not the case that if we can solve weak, let's say weak Z definability, we can immediately also solve weak Q definability. So there are sets that are definable, that are weakly definable in integer arithmetic, which are not weakly definable in linear rational arithmetic. So if we take, for instance, this formula phi here and interpret x over the integers, then what this formula defines is the whole line of the integers except the number 0, and this is obviously weakly Z definable by the formula that says x is not equal to 0. However, if we interpret x over the rationals, then we have a segment with infinitely many points between -1 and 1 that are not in this formula, and while we can rule out any finite number of points in formulas of weak linear rational arithmetic, we can't rule out an infinite number of points. And we'll later see a characterization that kind of lifts this intuitive idea onto a more formal level. So as a result, weak Z definability does not imply weak Q definability, and vice versa. Weak Q definability does also not imply weak Z definability. So if we take this formula here, and when interpreted over the integers, it says that all numbers below 0 are a multiple of 2, and all numbers above 0 are a multiple of 3. And this is a set that's not weakly Z definable. However, if we interpret this over the rationals, then this formula just defines the whole rational line, which is obviously weakly Q definable. Furthermore, it's worth mentioning that satisfiability reduces to weak definability, and for that reason, when we look at computational complexity aspects, we will restrict ourselves to the fragments which are expressively complete. So in the case of integer arithmetic, we look at existential formulas because they are expressively complete. So this follows from Pressburger's quantifier elimination procedure and the result of Ginzburg and Spanier that Pressburger sets are semi-linear. On the other hand, if we are looking at formulas of linear rational arithmetic, we'll just look at quantifier-free formulas, as they can define anything that is definable in full linear rational arithmetic. So this is a result of, this follows from Fourier-Motzkin quantifier elimination. The main results of our paper are as follows. We show that weak Q definability is co-NP complete, assuming that the input is a quantifier-free formula. We also show that weak Z definability is actually decidable in elementary time, and that the problem is hard for pi to p for existential formulas, even already in a fixed dimension. This hardness result is actually obtained by showing another problem, pi to p hard and thus pi to p complete, which is the universality problem for ultimately periodic sets given in generator representation. So these are also known as semilinear sets in dimension 1. So we establish a pi to p lower bound for this universality problem, which has actually been a very long-standing open problem in the theory of semilinear sets and was first asked in 1982 by Huynh. I will now give you some ideas how we obtain the co-NP upper bound for the weak definability problem for linear rational arithmetic. Let us take a look at the sets that we can define in weak linear arithmetic. So it's not difficult to see that these sets are finite unions of affine subspaces minus a finite number of other affine subspaces. So this follows from, if we're given an existential formula, we bring it into disjunctive normal form, then we'll see that each disjunct defines such a set. And if this set is non-empty, another observation that we can make is that these affine subspaces here on the right hand side can only cut out lower dimensional subspaces from this affine subset here on the left. Now, the sets definable in linear rational arithmetic, where we have the order relation available, are very similar, except that on the left-hand side we have polyhedra. Now, if we compare the left-hand sides of the weak and of the full linear rational arithmetic, then one major difference is that if we look at the affine subspace that this polyhedron lives in, inequalities allow us to cut out fully dimensional subsets from this affine subspace. So that's a major difference. In linear rational arithmetic, we can cut out fully dimensional parts of these affine subspaces. In weak linear rational arithmetic, this is not possible. Okay, so the key insight is that in weak linear rational arithmetic, we can only cut out a finite number of lower dimensional affine subspaces from a given affine subspace. And this basically gives us an idea why it is impossible to define this set here in weak linear rational arithmetic, because if we're looking at this affine subspace, that is the whole line, we're unable to cut out this continuous segment between -1 and 1 by just a finite number of points, because there are infinitely many of them. And now, if we are putting this characterization on a sort of more general level, then we come up with the following. So we're saying that a set X that is a subset of the rationals has the 0,1 property with respect to an affine subspace A if either X intersected A or A minus X is contained in a finite number of subspaces of dimension strictly less than the dimension of A. And using this definition, we can now fully characterize when a set that is definable in linear rational arithmetic is definable in weak linear rational arithmetic. So if we're given a set X that is obtained from a quantifier-free formula of linear arithmetic, then this set is weakly definable in linear rational arithmetic if and only if X has the 0,1 property with respect to all affine subspaces that are given by systems of equations whose constants are no larger than those in the defining formula phi. And so this is a full geometric characterization of when a set is weakly Q-definable. It also, in addition, enables us to get a decision procedure to decide weak Q-definability, because all we have to do is we can iterate over all these affine subspaces. There are only finitely many of them because the defining system of equations has bounded constants, and then we can just check whether the 0,1 property holds. And this is something that can be checked in polynomial time. This characterization unfortunately breaks when we're looking at integer arithmetic. So if we take a look at this formula here, which just defines the set of all even integers, then if we take as an affine subspace just a line here, then intersecting this set or taking the complement with respect to the subspace is not going to be contained in a finite union of affine subspaces of lower dimension, i.e. points. Okay, so we can't directly use this characterization that we've established in the rational case. However, what we can use instead to fill gaps of these kinds are so-called shifted lattices. So for those of you familiar with semilinear sets, they look very similar to linear sets, but we allow all the period vectors here to be multiplied by integer values. So as such, this defines a lattice, such a set. And then using these shifted lattices as a basis, we can essentially obtain an analogous characterization to the 0-1 property that we saw in the rational case, that together with some heavy machinery of semilinear sets, then in the end allows us to establish a characterization of weak Z definability that is very similar to the characterization we have for weak linear rational arithmetic. In the last part of my talk, I'd like to give you an idea how we obtain the pi to p lower bound for the universality problem of ultimately periodic sets. So recall that an ultimately periodic set is a subset of the natural numbers, such that we have an initial segment where we have no constraints on what the numbers in this initial segments are, but after a certain threshold, all the numbers in the set appear periodically. Now, of course, the question is, how can we represent such an infinite set? So we're looking at the representation in generator representation, which are basically semilinear sets in dimension 1. Okay, so this means that we're given a finite number of generator tuples, where each tuple consists of a base vector, which is just a number, and of some periods, and which are also just numbers, and there are only finitely many of them. And then we're looking over the union of the set that is generated by every generator tuple, which is just bi plus then all non-negative linear combinations of the periods. Okay, and the universality problem then asks whether this set U that is defined in this way, whether an ultimately periodic set is equivalent to the natural numbers. Now this problem was shown to be in pi to p because it is a special instance of the inclusion problem for semilinear sets, and Huynh showed in 1982 that this problem is pi to p complete. So this gives us the pi to p upper bound. In the same paper in which Huynh established this result, he asks whether the universality problem for semilinear sets, i.e. ultimately periodic sets in dimension 1, is pi to p hard as well, and this is another result that we've established in our paper. It is actually not too difficult to show pi to p hardness of the universality problem for semilinear sets in arbitrary dimensions once we have a good problem to reduce from at hand. So in our case, we're going to use a quantified generalization of the classical subset sum problem, which we showed pi to p complete a couple of years ago. However, when we want to move from arbitrary dimension to dimension 1, this becomes actually a little bit more subtle. In order to do so, we employ a technique that was made popular by Glover and Woolsey in their 1972 article. So what they show is that we can aggregate systems of linear Diophantine equations into a single linear Diophantine equations. So if we're given two linear Diophantine equations, Cxa and Dxb, then they showed that there are polynomial time computable numbers alpha and beta, such that this single aggregated linear Diophantine equation has the same set of solutions over the non-negative integers. However, this result is not strong enough for our purposes, because when we want to reduce from multiple dimensions into a single dimension, we need to essentially run this theorem on a couple of different systems of linear Diophantine equations. And what we show is that if we're given a family of systems of linear Diophantine equations where only the right-hand sides differ, then we can in polynomial time compute alpha beta such that they work for every pair of systems in our family of systems of linear Diophantine equations. So this is one of the corner points of our Pi2P lower bound. There are a couple of more details that you're very welcome to look up in the paper. This brings me to the end of my talk. So there are a couple of open problems that remain from our paper. Most notably, we've shown an elementary upper bound for deciding weak Z definability. The precise complexity is still open, so we're currently working out what the precise running time of the algorithm we've developed is. Another interesting open problem that's related to the questions we studied here is the precise complexity of weak linear integer arithmetic. So if we look at Pressburger's original article, then he actually studied this arithmetic theory and then only remarked that his quantifier elimination procedure also works when we have the order relation present. Now, as we've seen, weak linear integer arithmetic is strictly less expressive than Pressburger arithmetic, and this could indicate that it is computationally easier to decide, but at the moment we don't know, and this is unknown. I'm looking forward to hearing any questions that you may have during the online session. Until then, I'd like to thank the sponsors of this research and would also like to give image credits for the images used in this presentation. Thank you for your attention.